Hi everyone. As Hrant mentioned, I'm Rafayel Mkrtchyan from YerevaNN and Yerevan State University. Today I will be presenting our paper, which was accepted at a Big Data Service conference held by IEEE. It is called ML-based approaches for wireless and loss localization, input representations, and uncertainty estimation. Now, that may seem a complicated name, but we'll break it down in the next couple of minutes. So first, imagine we have antennas and we have a device. In this case, the device is located on the collar of this cute little dog. I'll use a base station and antenna interchangeably, and for a device I will also use user equipment. So our problem is to localize this device based on the radio wave information that are propagating from the device to the antennas. And in our particular case, we focus on the case when we have access to only one antenna. Now let's see what NLOS means. Its full form is no line of sight, and it's basically the case when there is a building or any other obstacle between the device and the antenna, and the radio waves propagate bouncing off of the buildings. Now let's get to some definitions. For each area, we have its top-down view of the map. We have the x and y coordinates of the user equipment. We have the x and y coordinates of the base station. And for each user equipment I and base station j, we have Kij radio waves. And each radio wave is described by 3 parameters. It is the time it took for the signal to arrive from the source to the destination. It's the angle at which it arrived at the base station, and it's the angle at which it departed from the user equipment. So to formulate our problem, we give our model the map, the location of the base station, and the radio wave information, and we expect it to estimate the location of the device. The first method we used was a multi-layer perceptron. For this case, we only used the shortest path. It is the one corresponding to the least amount of time it took for the signal to arrive. So for this case, we have 5 parameters: the x and y coordinates of the base station, and the time of arrival, the angle of departure, and the angle of arrival. We apply multi-layer perceptron with 3 intermediate layers of sizes 256, 1024, and 256. Now it has multiple drawbacks. One, we only use the shortest path, so we should design a method that could take into account more complex representations. And the MLP is not convenient for more complex representations, so the next approach we came up with is CNN with matrix inputs. In this case, the width of the matrix is fixed and its length is varying. So first we copy the location of the base station Kij times. Then we concatenate it with the radio wave information. First, we use 1D convolutions to process each individual path, and then we apply 2D convolutions to find patterns across multiple paths. Then we do average pooling, and on top of it we apply a fully connected neural network to get 2 coordinates of our device. The third method we used also takes into account the map of the area. So it is a UNet model applied in images. Our images have 3 channels. The first channel corresponds to the map. It's binary encoded, where 1 means it's a building and 0 means it's not a building. Our second channel corresponds to the angle of arrival. Here we draw lines starting from the location of the base station at the angle at which it arrived to the base station. And on the pixels of these lines, we encode the time of arrival information. On the third channel, we use the angle of departure information. So once again, we start from the base station location. We can't use the user equipment location because that's the thing we want to predict. And once again, we encode the time of arrival information in the pixels of these lines. We apply a UNAT model which gives us a heat map of possible predictions. Now for the dataset, we use the synthetic dataset called YereD, published by Huawei. It is based on maps of real urban areas, but the radio waves and the devices are simulated. Here we have 10,000 maps, and for each map we have 5 base stations and 30 user equipments. So for each map we have 150 pairs. Now to calculate the performance of our models, we use root mean square error and accuracy at x meters, which is defined as the proportion of the predictions that were inside x meters neighborhood of the ground truth. We will report our metrics on loss and NLOS cases separately. And here are the results. As you can see, MLP performs the best. CNN with the only one path, the shortest path, collapses to an MLP, so its results are in the same ballpark. CNN with 2 shortest paths performs almost exactly the same as the CNN with the shortest path. CNN with all paths performs the worst. And here are the results for the UNAT model. It might seem like MLP wins, but we have rich outputs for our UNAT model on which we can do analysis. So we can calculate an uncertainty score. We define it as the following. It's the number of pixels that are at least half as bright as the brightest pixel. We calculate it, we divide it into percentiles. We plot it on the x-axis, and on the y-axis we calculate the average RMSE for each bin. Now this is calculated for the NLOS case because it's our main point of interest. Here we can see the correlation between the root mean square error and the uncertainty score. As you can see, for NLOS it's spread, and for NLOS case it's more concentrated into a certain area. The rich predictions of our UNAT model also allow us to calculate top M location instead of just 1 locations. So how we do it? We subsample x and y coordinates according to the intensity of the pixel. We apply a Gaussian mixture model on top of it, and then we take the mean of each Gaussian. Now it has a drawback that the mean sometimes may be located in a black spot. To fix this, we align it to the brightest pixel in the square neighborhood of our mean. And here we can see the RMSE score for top 1 location on the y-axis, and on the x-axis on the left one we see the GMM means approach. And on the right side, we see the result of the GMM argmax approach. Now, on the right picture, we can see that GMM argmax beats the top 1 prediction in every single case. However, when calculating top X accuracies at 10, 20, 30, 40, and 50 meters, we see that GMM means performs the best. We also did ablation study of our input variables. Here we see that removing the angle of departure has the least impact on our prediction, and removing the angle of arrival has the most impact on our prediction. And also a quick hint at future work. We should validate our wrong predictions. So what does it mean? It means if our prediction was wrong, we should see if there was a user equipment in that location. Would its perimeters be similar to the ground truth location of the user equipment? And to do it, we have another part of the data released by YerevaNN. For 100 environments, we have one base station and 10,000 densely packed user equipment. So we can choose the closest one to our prediction and see if its perimeters are similar to the actual user equipment we were trying to locate. The next obvious thing to do is to improve the performance of our models. Maybe come up with newer models and try different input representations. Then we should test it on a real-world data. Like we create our model based on a synthetic data set. We test it on a synthetic data set, but we don't know how it will perform in real life. And the other problem to solve is the map reconstruction problem. It's like the inverse problem of this one. We have the location of the base stations, we have the locations of the user equipments, we have all the radio wave information for each pair. And based on this, we should predict where the buildings are. So to conclude, we tried several machine learning models with several different input representations. We saw that the UNAT model has rich outputs on top of which we can apply some analysis and also calculate top M predictions instead of one prediction. We also showed that the angle of arrival is more important than angle of departure. This is important because in real-life situations, we might not have information about the angle of departure. We might only have information about the time of arrival and the angle of arrival. And we also hinted at the future work. That's it. Thank you. And if you have any questions, I will be more than happy to answer.
Question. Could you please elaborate more on the map reconstruction problem?
Now, here we use the map as our first channel and the radio wave information on the second and third channels. Imagine we don't have the map. It is the thing that we should predict. We only have radio wave information about each pair. So like for each environment, we had 5 base stations and 30 user equipments. We have all the information about the locations of the base stations, about the locations of the user equipments. We have the radio wave parameters for each pair, and our problem is to reconstruct the map.
When you do the simulation, do you consider one user and one base, correct? Is there an interaction between different users? When you have multiple users, do they impact each other?
No, they don't interact with each other. The connections are directly from the user equipment to the base station.
Can you go to that slide where you had the scatter plots of GMMs?
Hmm?
Yeah, so here your y-axis is top 1 accuracy, right? And x-axis is top 5 or whatever, right? And if your point is above the diagonal, then it means that the accuracy was better in top 5, right? So you want all the points to be above the diagonal. But then we had few points below the diagonal on the left, and you said that's because the mean of the Gaussian mixture sometimes is off.
It's in a black spot where we don't have a higher intensity. So I think that explains why we see some points below the diagonal in this case.
But then in the table, the left one gave better scores if you fix the 5 meter threshold, 10 meter threshold, right?
Yes.
Small difference, okay. So it means that, can you go back? It means that probably like the benefit of these points is more than the
Ones below the diagonal.
yeah, the problems that come from these points. And if you do this other trick, all these things disappear. Oh, by the way, that was no line of sight. So here, orange is line of sight when you directly see the device from antenna, and blue is when it's behind the building. So the blue parts are the interesting parts. So the numbers that you showed are on the next slide. They are for all or for NLOS only?
I think these are for NLOS. These are for
so
NLOS.
these are for blue points. Okay, that's okay. Yeah. If we don't have more questions, let's thank the speaker again.